Good afternoon, everybody. Happy Monday. Glad to see everybody. Hope your Halloweens were interesting and fun or productive or whatever you wanted it to be. We are talking about electrophilic aromatic substitution some more, but before we get started with that, I want to give you a molecule of the day. So this is our molecule of the day. It's melatonin. I pulled this one out because, well, we just had the switch from daylight saving time to regular standard time, and if you're feeling a little off as far as like, groggy or I don't know, can't get to sleep, can't wake up, whatever, your circadian rhythms are a little off, could be due to this molecule not being quite balanced right now. This is a hormone responsible for regulating sleep-wake cycles, and it has an aromatic ring in it. This is a indole ring. It has a lone pair of electrons on the nitrogen, which are not basic because they're part of the 4n plus 2 pi electron system that's making this ring system aromatic. It in total has 1, 2, 4, 6, 8, 10 pi electrons. And this is one that you'll see over and over again in biology and in human health. It is got all kinds of substructures that are very similarly related that do other jobs. There's another nitrogen here that's got a lone pair, which is also not basic because it's attached to a carbonyl group. And so this one is not basic because the lone pair is shared with oxygen. Structurally similar analogs, if you've heard of the neurotransmitter serotonin, that's one that is very similar, just instead of this acyl group, it has a hydrogen, and instead of this methyl group, it has an H. So serotonin and melatonin are very, very similar in structure. This one's also somewhat similar to the amino acid tryptophan. So it's got, a lot of structural analogs, but it's our molecule of the day. So there we go. Now, if we're gonna chat about electrophilic aromatic substitution some, this question, it's a survey question, relates to Friedel-Crafts alkylation reactions and rearrangements that we talked about last time. Let's chat about some of these cations here. So there's a series of 5 cations here, and it's asked which cannot rearrange to become more stable. So I want to go through all of these just to give you a little bit of review on carbocation rearrangements. So I'm going to draw each one of these over on the board next door, and then we'll talk about them and show what rearrangements they can do and what rearrangements they, would not want to do if there's one like that. And there is one up there that won't rearrange. So I'm going to go over these individually and chat about them. I suppose the first one we should talk about is probably structure A, since it's over there on the left side. So here is structure A. It's a 6-membered ring that has a carbocation here. Now this is already a tertiary carbocation, so this carbocation is already pretty stable. And one of the thing about this question, it asks which one cannot rearrange to become more stable. This one won't be more stable if it were to undergo some kind of carbocation rearrangement. If you look at the things that are next door here, there are 2 H's on that carbon. Migrating one of those over would give a less stable secondary carbocation, so that's not gonna work. Over here on this carbon, there are 2 methyl groups. Migrating one of those over just gives really the same carbocation. So this one doesn't result in a more stable carbocation. It's not going to undergo a rearrangement. That was the thing last semester when we started talking about these rearrangements, is it has to go from less stable to more stable, from higher energy to lower energy for the reaction to want to occur. So this is actually the answer, is A is the structure that can't rearrange to become more stable. So all the others can. So let's take a look at structure B, for example, and see if we can document how that one can rearrange. This one's got this structure, and there's a carbocation here in that position. This is a secondary carbocation, the structure B. And if you look next door over here, on the carbon that's next door here, there is a hydrogen. And if that hydrogen were to move over via a 1,2 hydride shift, that would produce a new carbocation where the cation is on now a tertiary position. So it goes from secondary carbocation to tertiary. So that's definitely more stable. That's a 1,2 hydride shift. So B would definitely want to rearrange to become more stable. Then if we look at structure C has 2 methyl groups right there. There's a methyl group here, and in this structure the carbocation is up here in the upper left-hand corner. Here, there's no H here that would want to move over because that would give a secondary carbocation, but if you look at this carbon, if one of these methyl groups were to move over, that's a 1,2 alkyl shift. That would give a carbocation that's more stable. That would give a tertiary carbocation. So this is another one that is going to want to happen because it produces a more stable carbocation from a less stable one. So it goes from secondary to tertiary, which is a good deal. Maybe what I'll do is just I'll put a label C on this one, then we'll talk about D. Structure D has the same carbon skeleton as the others. It's got 2 methyl groups there and a methyl group here, but it's got the it's got the cation in a primary position, which is very unstable. That's an awful place for a carbocation, and if this carbocation were to like come into existence, it would not stay like this for very long at all. It would very quickly want to rearrange, and it would do that by this hydrogen here moving over, doing a 1,2 hydride shift. That would take it from a primary carbocation to a tertiary carbocation, which is a really big increase in stability from primary to tertiary. So that's a really good move for the molecule. It becomes a lot more stable. And then finally, the last one here is one where the molecule is a little different than we've seen in the past. There are the same carbon groups, but this one has a double bond, right? I just want to double check on this. Yep, it's got a double bond here, and there's a cation here. So this is structure E. This is a secondary carbocation, and it doesn't look like the others in that there's no hydrogen or carbon next door that can obviously create a more substituted carbocation. Over here, having one of these migrate would give a secondary carbocation in that position, which isn't more stable. If one of these H's were to hop over, it would give a different secondary carbocation, which you might think isn't better, but if you look at the position of where that's going to be, next to the double bond means it's going to be resonance stabilized. So this is actually going to be a move towards a much more stable carbocation because you go from one carbocation that's secondary with no resonance to when the hydride shift happens, you get a carbocation that's now conjugated, and it's going to be delocalized, and it's going to have a resonance structure. This one's going to be a lot more stable. So this one is secondary with resonance. So that helps its stability a lot. So the rearranged carbocation is a lot more stable. So do you have any questions about these? So the thing to look for and think about for this chapter is if you had alkyl halides where there was a chlorine in place of where the plus charge is, you put it in with aluminum chloride and try to do a Friedel-Crafts alkylation reaction, you'll get a carbocation, but then it might rearrange. And so these are the things to think about. Think about, draw the initial carbocation that would form, and then ask yourself, is there a way for this carbocation to rearrange to become more stable? If there is, then it's going to want to happen. So, all right. That's the survey question. And for statistics, I'm just going to take a look at that and see how the class did, because I haven't looked at that yet. Well, it was a popular answer A, but it wasn't a lot of consensus about that A should be the correct answer. There was a lot of people that selected D or E, which I think I can kind of understand. I think what this means is that B and C were less, were less popular. People could clearly see these were ones that could rearrange to become more stable, but it looks like the class had a little bit more trouble understanding the D and E, the rearrangements that they would undergo, which is kind of predictable, I guess. So just this expands your I guess, ideas about rearrangements that can happen. So I guess it's good practice for that. Any questions about the survey? All right. Well, let's talk about substituted benzene rings some more. So last time we left with this concept of benzene rings, when they have a substituent on them, a group on the benzene ring, that affects their reactivity. And it does two things. It affects the rate at which electrophilic aromatic substitution will occur, can make it faster or slower, and directs the substitution to specific spots. So just as a review from last time, we looked at toluene, and rather than just focus on toluene, I'm going to put an R group here and say that R is equal to any alkyl group. And what alkyl groups do is they donate electron density into the ring inductively. So alkyl groups push a little bit of electron density into the ring, and they make it a little bit more electron rich than it would normally be. So alkyl groups donate electron density inductively. That means through sigma bonds. And what that does is makes the ring more reactive. Because the ring's more electron rich. And so it's going to be more reactive in electrophilic aromatic substitution. And specifically, it donates electron density into the positions that are ortho and para. So it makes the ring more reactive and directs to ortho and para positions. So there it is. Alkyl groups do that. We're going to look now at a whole host of other groups that do activating or deactivating. So what I'm going to do is I'm going to put up on the screen that list of activating and deactivating groups from the textbook that I put up last time and which I'm going to give to you as a resource on your next exam. And let's just go through them and take a look at them. So there's a big list of activating and deactivating groups on this chart. And I will scroll a little bit and maybe try to get them to all fit. There we go. So we've got our activating groups up here, which are above at the top of the screen. And the ones that are the highest up are the most activating. And then they get weaker as you go down. Then there's the halogens, which are represented by X, and that's fluorine, chlorine, bromine, and iodine. They are weakly deactivating groups. They slow down electrophilic aromatic substitution, but not tremendously. And then below that are the really strongly deactivating groups. And those are ones we'll talk about in a little bit. But for right now, what we're going to do is try to focus on these up here. Why do these do what they do? Why are they activating and ortho-para directing? They're strongly activating and ortho-para directing. We have the R group down here, the alkyl group, but now we're going to try to figure out all these others. And the one thing that you'll notice if you look at these is that the group that's attached directly to the ring, nitrogen, oxygen, oxygen, nitrogen, they have lone pairs of electrons, at least one lone pair of electrons, and that's the key. That's what makes them behave the way they do. And so now we're going to take a look at the two ways that groups like this affect the ring. So they have kind of a split personality. They will push electron density in through a resonance effect, but they also pull electron density out through this inductive effect. So we're going to look at both effects, and then we'll talk about which one is more important. So I'm going to come over here, and we'll talk about the one that's at the top of the list, aniline. So aniline is a powerful activating group. It is the most strongly activating in the entire list, and we're going to talk about it. So this is aniline with a nitrogen and a pair of electrons. So this does two things. Two effects. Electron withdrawing inductively. And that, I think, makes sense because you know that nitrogen is more electronegative than carbon, so it has this electron sucking effect, and that transmits to the ring. So nitrogen gets a partial negative charge, and then that carbon gets a partial positive charge, and the partial positive charge is transmitted to the other carbons, but it gets weaker every atom that it goes through. So every bond it gets further away from the electronegative element, it decreases because it's a through distance effect and it falls off over distance. So that's an effect. The other effect is electron donating through resonance. And I know there's questions in the homework that ask about this because I just went through the homework and I looked at all the questions, and there's a bunch of them that ask you to classify substituents. What is their effect inductively? What do they do through the sigma bond? Well, this one withdraws electron density, but they're electron donating through resonance, and the way that works is that the nitrogen lone pair can donate its electron pair in through resonance. So you can take an arrow here and push it in to share it between carbon and nitrogen, and then a pair of electrons in the ring go and land on the ortho position. So this generates a resonance structure where the ortho position, one of the ortho positions, has a pair of electrons and a formal minus charge. Okay, so it's clearly showing how the effect of this nitrogen is to make that ortho position more electron rich. That's not the only resonance structure though. So you can draw another one if you take that pair of electrons and push it further along. The electron pair in this carbon-carbon bond can get pushed out onto the para position. So this resonance structure shows the lone pair now on the para position. So now we've got a lone pair and a formal minus charge in the para position. So this resonance structure is saying, hey, para position is pretty electron rich too. And then you can push the electrons even a bit further to land them on the other ortho position. And that gives this picture where the other ortho position now has the formal minus charge and is electron rich. And so these are all resonance structures of aniline. And if you were to just draw one picture that tried to summarize all of this, the picture that you would draw would be one where you try to incorporate all of these different aspects into one picture, which I would say would look like this. You draw the aniline and say, well, there's partial negative charge at the ortho position, the para position, and the other ortho position, because you've got these resonance structures that are saying that. So the effect on the ring from the nitrogen from resonance is that it makes the ortho and para positions more electron rich. And it turns out that this is the most important effect. And this electron withdrawing inductively is more of a minor effect. It doesn't really dominate the characteristics, the ring characteristics that you get when you put an amino group on. It really is mostly about the donating through resonance. So when you see a nitrogen with a lone pair attached to the ring, think that lone pair can be donated into the ring to make a ring that's really electron rich. So overall, electron rich. So it has a lot of electron density. When it sees electrophiles like a E+, like one of those activated electrophiles, active electrophiles we talked about last week, it really wants to react, and it wants to react specifically through the ortho positions and the para position. Overall electron rich and ortho para directing. And this behavior really describes all of the strongly activating groups that are in the chart. They'll either have a nitrogen with a lone pair attached to the ring, or they'll have an oxygen. So if you wanted to go through the same logic and you just replace this NH2 with an OH, there'd be two lone pairs. You could take the lone pair off the oxygen, draw three similar resonance structures to show how the oxygen donates electron density in. So they're all really strongly activating and ortho-para directing because they've got a lone pair of electrons on the atom that's attached to the ring, nitrogen, oxygen, oxygen, nitrogen, that can be shared with the ring. And the reason that they are arranged the way they are, nitrogen is more reactive or more activating than oxygen, is that nitrogen is less electronegative than oxygen. So nitrogen is more willing to share a pair of electrons, whereas oxygen is more likely to want to hold on to them because it's more electronegative. So you see the pattern goes nitrogen, then oxygen with no group on. Then you put a group on this one, it doesn't really change it very much, but when you start putting on like a CO carbonyl group, that tends to make it less electron rich. So I want to go through a few of these like specifically because people tend to get confused about these, like what is that and how does it work? So let's compare a couple of rings that have these different substituents on them. I'm going to draw them out, and then we'll talk about why the hierarchy is the way that it is. So the most strongly activating was the aniline. Then, so I'll put that down. Then the next most strongly activating was phenol. Phenol's got lone pair of electrons on it, on that atom that's attached to the ring. So it donates electron density in. The next one that's listed is anisole, the OCH3, and this one is, I would say, about the same. It's not really that different. It's listed as less reactive, but yeah, I'm going to say, I'll put that down just so it's not confusing, but it's in sort of the same class. It's pretty strongly activating. Then you get to this molecule. So this molecule is got a nitrogen on it that has an H, but the other thing it's attached to is a carbonyl group. So the lone pair of electrons, that nitrogen is still attached to the ring. It can still push electron density into the ring to make the ring more electron rich. But this carbonyl is also pulling electron density away from the nitrogen. So the nitrogen, in addition to sharing with the ring, is also sharing with this oxygen of the carbonyl group through resonance. And so this lone pair is a lot less able to share its electrons with the ring because it's already sharing a lot of electrons with the carbonyl. So this one is less reactive. This nitrogen is less reactive than these others because of the carbonyl group consuming some of its electron density. And then this one isn't in the chart, but it follows logically from the argument that I just talked about. I'm going to see if I can get a little bit more board real estate here. Make this sign a little different. And I'm going to make this ring kind of a little bit skinny, and then I'm going to put an oxygen here attached to a carbonyl group. This one is an activating group. It's just less strongly activating than any of the others because it has an atom attached to the ring that has a lone pair that can be shared in through resonance to activate the ring. But it's an oxygen, which means it's more electronegative and less likely to want to share than nitrogen. And it has an oxygen carbonyl that is pulling electron density towards it as well. So this is a weaker activating group. So this is weaker activating group. And this is the stronger activating group. It's the strongest one we're going to see. And then the order is like that. So the reason we're talking about this in some detail is because the ordering of the activity matters later on when we start talking about where does a reaction happen on a ring. Sometimes there's issues where a ring might have more than one group attached to it, and we're going to learn rules. Like one of the rules is the strongest activating group wins the argument, basically. If you've got two groups on a ring and you're not sure which one is going to influence the reaction the most, it ends up being the most reactive group, the most strongly donating group. So the ordering makes a difference for predicting products. All right, well, let's take a look at the next things in the list here. I'm going to flash back here to the list of groups, jiggle the mouse a little bit so the computer doesn't go to sleep on me, which I hate, but happens a lot. Okay, so now we go down to the halogens. So halogens have an X group. So that atom attached to the ring does have a pair of electrons. And let's talk about these then. Let's dive into that. These are going to end up being withdrawing overall, but ortho-para-directing. So we're going to talk about those over here on the screen, try to understand how they behave. So when you have a benzene ring that has a halogen on it, it's got three, the group has three lone pairs. So X is equal to fluorine, chlorine, bromine, or iodine. There are two effects. One is the inductive withdrawing effect. Inductively withdrawing. Electron density, with electron density. So it pulls electron density out. And that's got a deactivating effect. Then it donates electron density through resonance. So this is kind of the same description that we had with the previous groups we looked at, the strong activating groups that were, they removed electron density inductively through their sigma bond, and then they pushed electron density in through their pi bond. The difference here is that this is the major effect. And here, this is the minor effect. So they are overall electron poor. The two effects don't quite cancel out. Overall, X is a mild deactivating group. but is ortho-para-directing because it's still got the ability to donate electron density in through its lone pair. So it can push a lone pair of electrons in and they'll land on the ortho position, and then you can push them along to push them into the para position and to the other ortho position. So that's making those positions partially negative. But overall, the ring on a whole is more electron poor than benzene itself. So they're weakly deactivating groups, but ortho-para directors. So that's halogens. They're in a special class by themselves. Then, if we look at this chart over here, we can look at the last class of groups. And that's the ones below the dotted line. So these are all what are called meta-directors. And they're strongly deactivating groups. So all of these that are below the dotted line, those are strong deactivated groups. They really deactivate the ring a lot. They have no electron donating ability whatsoever. They just pull electron density away. And most of them, when you look at them, you'll see when we start drawing structures of these, they have a common theme. Carbonyl, 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 carbonyl. That's C double bond O. So a carbon that's doubly bonded to an electronegative oxygen. CN is C triple bonded to nitrogen, which is an electron withdrawing element. And I'm going to go through these and talk about these, but they've got very common structural threads that help to explain why they behave the way they do. So let's talk about these electron withdrawing strong deactivating meta-directors. This is the last class of groups. So here is an example of an aromatic ring that has a carbonyl group attached to it. It's a C double bond O and then something else. I'll put R here. R could be hydrogen, it could be a carbon group, that'd be aldehyde ketone. If you put an O here, it could be OH, and that could be carboxylic acid or ester. So many different carbonyl containing molecules. The reason that this is a strong deactivating group is because this oxygen right here has an electron sucking effect on the electrons on the ring. So a pair of electrons in the ring can get pulled out by the carbonyl oxygen, and that gives, as a resonance structure, this molecule, which has got a pair of electrons removed from the ring and given to this oxygen that sits outside the ring. So now the ortho position's got a formal positive charge on it. So that's saying that ortho position has gotten a lot of electron density taken away through resonance by the carbonyl. You can draw another resonance structure where you push that pair of electrons over one, and then you move the positive charge out onto the para position. So this is another resonance structure where now it's the para position that's got the formal positive charge. So that resonance structure is saying, hey, a para position is pretty electron poor too. And you could draw another resonance structure where you see the ring with a positive charge in a resonance structure on the other ortho position. So the ortho positions are being deactivated. The para position is being deactivated. So here's a resonance structure that explains why the other para position is electron poor. And these all are forming a collection of resonance structures that are helping to describe the nature of that molecule. And if you had to draw one that showed what was going on with the ring, here's a resonance hybrid structure that does a pretty good job of explaining it. It's like the ring has this characteristic. It's got partial positive charge on the ortho position, the para position, and the other ortho position. So if you're an electrophile and you're approaching this molecule trying to decide where to react with it, you're positively charged if you're an electrophile. The places you're not going to want to go are the ortho and para positions because positive charge repels positive charge. The electrophile's best option with this molecule is to hit the meta positions, because those are at least not deactivated. So these groups are strongly deactivating and meta-directing. And it's not that the meta positions are activated or are particularly electron rich. They're just not electron poor. With these strongly deactivated groups, the group's effect is to deactivate the ortho and para positions, leaving the meta position as the best option for an electrophile. So the big thing with these is they're strongly deactivating through resonance. There are two effects. Again, electron withdrawing inductively. So if you look at the through bond effects, the oxygen on the carbonyl pulls electron density towards it, which pulls electron density away from that carbon, which pulls electron density away from that carbon. And the ring is more electron poor because of that effect. But then there's also this resonance effect, electron withdrawing by resonance, which is the whole point of the set of resonance structures I drew up here. And that's really the major effect. That's the one that really explains most of what is going on with it. And this one is more of a minor effect. So any structure that you can draw that has an electronegative element bonded to a carbon that's bonded to the ring can have this effect. Let's take a look at a few of the other ones that aren't listed. Oh yes, there's a question. Oh, you mean the groups? It's what they do to the electron density on the ring. So the question is why are they called activating or deactivating groups? It has to do with what is the net effect of that group on the ring. Does it push electron density in? If it does, it's an activating group. If its net result is to pull electron density out, then it's a deactivating group. So does that help answer the question? Okay, so strongly deactivating means it's making the ring more electron poor. It's pulling electron density out. The ring develops partial positive charges. That deactivates it because the thing it's reacting with is an electron poor species. So if you want the best reaction, your electrophile would be really electron poor and your ring would be really electron rich. And then they're likely to want to get together. But this ring is not very electron rich. So an electrophile might still react with it, but it's not going to be as good a target for it. It's not going to be as attracted to it because there's just not that big a difference in charge between them. You've got a positive thing reacting with a partially positive thing, and that's not it doesn't give you the strongest attractive force. So that's the nature of that. And let's talk about some of these other groups. If we go over here and look at what's in the chart over here, we've got, these are all the ones that contain carbonyls. They're C triple bond N, S with double bonds to oxygen, N with double bond to oxygen, and then N with a positive charge. We're going to take a look at some of these now and just talk about why they are electron withdrawing, just so you can have an appreciation for that. So C triple bond N, that's a nitrile group. The reason this is electron withdrawing is that group can pull electron density out of the ring, put a partial positive or full positive charge there, and then that gets communicated throughout the ring, basically making the ortho and para positions electron poor by through resonance. Then there was another one, the sulfonic acid group, that has this structure. So sulfonic acids are electron withdrawing because through resonance, they can pull electron density out of the ring like that. They are making that position partially positive through resonance, and then there are resonance structures that make those positions also partially positive. Then let's see, we had nitro group was another one that was listed. Nitro is a powerful electron withdrawing group. It's really intensely deactivating, and the reason is that it's got a full formal positive charge on nitrogen and those two electronegative oxygens attached to it. So this molecule, this group, has a tendency to pull electron density out and make the ortho and para positions very electron poor. So those are deactivating groups that are really powerful, and then through resonance. And then there's a couple others that I just wanted to point out as well. The one from the list has nitrogen with three other things. They could be hydrogens, they could be carbon groups, but this just, since it's got a full formal positive charge, it's got a very strongly electron withdrawing effect through inductive effect. And then one more, because it appeared in the homework when I was looking through the homework today, so I want to point out what it does. Trifluoromethyl. This is one that if it doesn't appear in the list, you could probably predict what's going to happen, because fluorine is the most electronegative element. So those fluorines are all pulling electron density towards themselves and away from this poor carbon here, which is very electron poor. And then that carbon in turn steals electron density away from the ring, and that through bond effect transmits throughout the ring. So these are all strongly deactivating groups. The top are electron withdrawing through resonance. These bottom two are electron withdrawing through this inductive effect. So you've got the list, but knowing how to use it and understanding why is also one of the important kind of points. Okay, so we'll work on this, practice reading the table and predicting reaction products and all of that. The next thing that comes up in the chapter is talking about some limitations of some of these reactions that we've been talking about, based on what we now know about the activating and deactivating effects of all these groups. So this is a section that talks about limitations of substitution reactions. Limitations of substitution reactions. So we learned all these electrophilic aromatic substitution reactions. And now we know something about directing effects. And so the way that groups influence the reactivity can be pretty profound. So we're going to look at a few classes here. So the first class of, I guess, effects to worry about are limitations with halogenation on strongly activated rings. Limitations on halogenations with strongly activated rings. So overreaction is sometimes a problem. Overreaction is a problem. That's the limitation. So let me show you what happens when you try to do a halogenation reaction on one of these very strongly activated rings. So like, for example, aniline, which is a very activated ring. It's the most activated ring. It's got partial negative charges in these spots. if you do a halogenation reaction where you try to put a chlorine on the ring, and the way you would do that is you'd select the reagents Cl2 and then a loose acid catalyst like FeCl3, and you might be hoping to get one chlorine on the ring, and you'd expect it to go ortho or para because that's the nature of this group. But what happens here is that it reacts with all the positions. Rather than just once, it reacts 3 times. And so you get chlorines in all the reactive positions. So this is overreaction when you want one to go on, but instead you get 3 going on. So it's a problem because this is just a really, really reactive group. Okay, I'm going to move over to the next board and talk about 2 other substituents where it's also a problem. The next 2 down in the list, phenol and ethoxy or methoxy groups, alkoxy groups, it also is a problem. So we're going to talk about those. But with those at least, there is a potential way around it. So if you have a phenol, for example, or you have an R group in place of the H. So what I'm saying here is it could be either an OH or it could be an O with an R group. These are going to behave similarly in that if you put in chlorine and FeCl3, because these are very strongly activated rings and they're specifically activated in the ortho and the para positions by resonance due to the lone pairs on that atom, you're going to get a molecule that's got chlorines in all the positions that were activated by the group. So overreaction. Here is one way around it though. With OH and OR substituted rings, overreaction can be fixed or solved can be avoided is probably the best word to use here by just leaving out the catalyst. Leaving out the catalyst. And we've been using FeX3, FeCl3 usually for chlorination and FeBr3 for bromination. Here's the idea. Catalysts make the reaction go faster. This reaction has a problem going too fast and going too far. So you can slow it down. If you take the catalyst away, it backs off the reactivity enough so that the reaction will occur once, but not 3 times. So here is the result that you would get if you do the reaction this way. So here's an example. If you take a phenol, that's a ring that's got the OH group on it, it's activating the ortho and para positions by putting a partial negative charge on them. If you simply put the halogen in there, it could be Cl2, could be Br2, and then just let the reaction go, but no catalyst. You'll get a mixture of monosubstituted rings. You'll get the halogenation occurring in the ortho position, which is one of the 2 possible mono substitution products. And you'll also get the para as the other major product in this reaction. So I'll say here mono substituted products are what you get. So it's a useful trick to be able to do. It's a way to control what you get out of a chlorination or bromination reaction. You have a little bit of control over it anyway. Right, the next class of reaction that we're going to talk about limitations for are the Friedel-Crafts reactions, and there are a bunch. And Friedel-Crafts reactions have a bunch of limitations. They're really useful, but they're also kind of complicated. So this is the second class of problems. It's limitations with Friedel-Crafts reactions. So there's limitations that affect both, for example. So limitation number one is that they fail with strongly deactivated rings. So there's that big list of strong deactivating groups that were meta-directors. If the ring has one of those meta-directors on it, it's too electron poor to react via Friedel-Crafts reaction. So Friedel-Crafts reactions don't work with strongly deactivated rings. They'll work with halogenated rings, but not one of the groups that's strongly electron withdrawing. So that's issue number one. The other issue is, one of the other issues is they don't work with anilines. And that might be a bit counterintuitive. Well, it's really counterintuitive because that's benzene ring that has the NH2 group, because that's the most activated ring. So here's the problem. It's like it's too reactive. So here's the reason. The explanation is anilines aniline reacts with the AlCl3 catalyst. And so this is the problem. So if you put, like, imagine you were trying to do this Friedel-Crafts alkylation reaction. You had aniline, and then you had maybe like a alkyl halide, like a chloroethane, and then you had aluminum chloride, because that's the recipe that you'd follow. What you need to have happen is you need the aluminum chloride to bind to the chlorine. So you might want that to happen, but it turns out that the electron pair on the nitrogen is a sort of a juicier target for the aluminum. The aluminum's picky. It's partially positive, but you know, it's got two different kinds of atoms here that have lone pairs it could go after. Chlorine is more electronegative. It holds on to its electrons tighter. It's not going to share them as well. That nitrogen, it's less electronegative. It's more willing to share. So what happens is, instead of the chlorine binding to the aluminum, which is needed to activate it, the aniline goes there and it sticks to the nitrogen. And now you've got a nitrogen that is no longer activating. It has an aluminum that's attached to it. It's putting a big partial positive or full formal positive charge on the atom attached to the ring. So we went from the most strongly activating group to really the most deactivating group that we know of. So this is unreactive. So there's two problems. The first problem is the aluminum isn't going to stick to the chlorine to activate it, which you need to have happen. And the even bigger problem is instead it sticks to the nitrogen and it makes it no longer an electron releasing group. Now it's an electron withdrawing group. So that's the first two limitations of Friedel-Crafts reactions. When we come back on Wednesday, we'll talk about a few more, because there's a few more. Sorry, they're useful, good reactions, but they've got their limitations. So we'll talk about that next time.